Welcome, engineers. My name's Travis IQ, and today we're going to talk about a security topic, encryption. Now, there's a number of facets of encryption that we can talk about, and we should probably define encryption to start, right? So encryption is the act of obfuscating data, right? Oftentimes we'll talk about generation of pseudo-random strings, and what we mean by pseudo-random strings are strings that appear random, right? But they are not random. Pseudo-randomness. If they were completely random, then we would have no way of returning those pseudo-random strings back to clear text. And so we talk about clear text and ciphertext being two of the pieces of terminology that we'll talk about here in our encryption section. Clear text and ciphertext. And so what we do is we use a cryptographic transformation to turn our clear text into ciphertext, and then to turn our ciphertext back into clear text. Notice I didn't give any context as to when or where we would do this, right? So, for example, we can use encryption to encrypt data in transit, right? Data going from one place to another, and we don't want Eve eavesdropping in on Alice and Bob's conversation. That's a good way to think of encryption, sure. We could also encrypt, so this is in transit. We could also encrypt data at rest, right? And so this would be data in storage, right? Or on some sort of HDD drive. I tried to do my best for an HDD drive drawing there, and it just did not work, unfortunately. Each of these encryption mechanisms or areas of encryption have their own requirements. Specifically, in this use case here, we have the issue of key exchange, in-band key exchange. How do I, Alice, tell Bob how we're going to encrypt and decrypt this data set? We'll get to that. Let's think about some obvious obfuscation mechanism. All right, so how do we encrypt data? What I'm showing here is a substitution cipher. And what this means is I take one letter and I substitute it with another letter. Right, so in this case, a T is always going to be substituted with an E. An R is always going to be substituted with an L. An A is always going to be substituted with a C, and so on and so forth. This is a very simple cipher mechanism, and clearly our cryptographic ciphers that we use in cybersecurity these days are not nearly as simple, right? They may incorporate components of substitution or transposition ciphers, but they are significantly more complex than what I've shown here. This is just to illustrate the fact that we can use different cipher mechanisms to obfuscate the data. And here's my clear text, and here's my ciphertext. Okay, Travis, that sounds pretty simple. How do I implement this in the real world? In the real world, what we have is our more simplistic mechanism of encryption is known as symmetric encryption. And so symmetric encryption utilizes the same key. So this would be key 1 and key 1. And a key is a string of bits that determines how the cipher transforms the plain text into the ciphertext. So that's what it is. We'll take a look at this in an example in just a second, but that's what this key is. It's a string of bits, generally represented in hex, that determines how the cipher transforms the plain text into ciphertext. In this case, we use the same key to both encrypt and decrypt. So Alice takes her message, hello, utilizes this key and the cipher to generate some ciphertext, 1246, sends this to Bob. Bob uses this key 100100100100111, uses this key and the cipher that they agreed upon and transforms this ciphertext into clear text. And Bob gets the message. He says, oh, Alice says hello. Simple enough. Not necessarily. We have to agree on a cipher. So we have to agree on how we're going to integrate these keys. We also have to agree on a key. So how does Alice tell Bob, hey, I want to use this key over here. Let's use something different. Let's say the key is taco. Wow. Alice says, hey, the key is taco. Okay, now Bob knows it. But what if Eve is listening in here? Yeah, so this is an issue. We call this in-band key exchange. How do I get this information to you so that we can then encrypt the data and the person listening in on this line won't know what the key is? You know, I don't actually have this problem if I'm not transmitting data over a wire, right? If I'm encrypting data at rest, let's say I'm encrypting data on a drive, on an HDD drive, I actually don't have this problem at all because I don't have to exchange the key with anyone. So if I were to use something like BitLocker for full disk encryption, BitLocker uses a symmetric algorithm. What symmetric algorithms are there? There are some older symmetric algorithms like the data encryption standard, DES. There is another older algorithm but newer than DES, triple DES. Basically the data encryption standard run 3 times. This makes sense. And then there is an algorithm that we use every day now, which is AES. This is the advanced encryption standard. And AES supports variable length keys. So let's just say 192-bit key here, for example. BitLocker actually uses 128-bit keyed AES by default. This is an example of a time when we would use a symmetric algorithm and have no problems at all. Okay, how do we exchange this information in band though? So how do I get this information to someone over the same media that Eve is listening in on without Eve being able to determine what's going on? We have another branch of cryptography. This is known as asymmetric encryption. Symmetric encryption being symmetrical keys, the same keys. Asymmetric encryption being different keys. So on this side we have key 1, and now Bob uses key 2. Asymmetric encryption also has another name. Asymmetric encryption is also oftentimes known as public key, private key. And so in this case, Alice and Bob, Alice can encrypt using her private key, and Bob can decrypt Alice's message using Alice's public key. Now the direction I just showed you here, going from this direction to Bob, actually isn't a private message, doesn't maintain confidentiality at all, because public keys, as the name might suggest, are just that, public. So anything that Alice encrypts with her private key, anyone can decrypt knowing her public key. And her public key is publicly available. Where you publish this public key and the use of certificate infrastructures or things like this are going to be saved for a later date. But just know that public keys are just that, public. So if Alice were to send a message to Bob that said, hey, I want to use the asymmetric key taco, then anybody with Alice's public key, who is everybody, Eve included, could listen in, decrypt the message, and determine what the symmetric key that they were going to use is. Okay, Travis, you didn't fix the problem. You told me that a good example of when we would use public key, private key is for in-band key exchange, right? And then you just told me that in this direction, it actually doesn't work that well. It doesn't work at all. Okay, let's go in the opposite direction. Bob has Alice's public key. Bob sends a message using Alice's public key to encrypt the message. And Bob says the password is taco1. who can view that message. If the data was encrypted with Alice's public key, the only key that can decrypt that message is Alice's private key. Now we have a solution. Private keys are, just as the name suggests, meant to be kept private. If you were to expose a private key, you should immediately remake the key pair and keep the private key as private as possible. Private keys are very important. It is very important to keep private keys private. So now Bob can send a message that Eve cannot read, and Alice can decrypt. We can then go on and use a symmetric algorithm, let's say AES 128, to exchange information. I'm going to get into why we would use a symmetric algorithm over an asymmetric algorithm, but what I'd like to do before that is show you some examples of asymmetric algorithms. So RSA, that's a very common asymmetric algorithm. ECC, Diffie-Hellman, these are all common examples of asymmetric algorithms. So I can use, for example, RSA for key exchange, and then what? AES for what we would call bulk encryption. Why would I use AES for bulk encryption and not just RSA? That's what you're asking me, right? You're going, Travis, why wouldn't I use RSA for all of my encryption if it's going to work so well? Because asymmetric algorithms are computationally less efficient. And if we're exchanging a lot of information, like let's say on the internet, then I probably want to use a more efficient encryption algorithm to exchange the bulk of my information. That's why we call this a bulk encryption algorithm. And I'd like to use the less efficient algorithm for the setup of the link, the exchange of the keyed information. There's a lot of additional information that goes on here, and there's some other topics within the public key, private key infrastructure, the PKI infrastructure that we could touch on here. But I wanted to introduce to you the concepts of some key components of encryption at this point. With that being said, let's take a look at an example. One of my favorite sites, CyberChef. If you haven't taken a look at it, please do take a look at it. It's an encryption and hashing and decryption site that uses a web interface. It's actually really great for it's great for demos. It's also great. I know a lot of people that will use this web interface for simplicity's sake. If I wanted to show you the obfuscation of an input like Travis IQ, this is the result of Travis IQ encrypted with some random symmetric key and an initialization vector using triple DES. You will notice that the input looks nothing like the output. So this is the clear text, and this is the ciphertext. That being said, that's my introduction to encryption and encryption algorithms. And as always, engineer, break stuff, and have fun.